And not important to me.
Okay, that's welcome.
Well, I'll say you all hope it's a once-in-a-lifetime show. I asked GIovanni to help me because I only have the hand-eye coordination to write stuff on the chalkboard and barely at that. So I need him to juggle for me. So today I decided to talk about something that's kind of a bit fun. And, we get to count stuff, which is better than all the continuous shit that's been going on recently. And GSS. We like our things discrete. So let's talk a little bit about the math of juggling. So the first thing is we need to define kind of what we mean by juggling. And I'll ask GIovanni to come up and demonstrate a couple things. Yeah, can you come up? So the first, we're going to make a couple assumptions that'll kind of help us out a little bit. And I'll demonstrate why these are practical assumptions. So, number one, we've been juggling forever and will continue to do so. We're not going to worry about how you start juggling. We're not going to worry about how you end juggling. We're just going to care about the patterns that actually happen in between. So we've been juggling forever, just like GIovanni's going to do. Woo! And continue.
That's not continuous shit. Oh my god.
Oh no. Fail. Number two is that we're going to juggle along to a constant beat, where we throw and catch a ball at any beat. So we juggle to a beat. And three, what we do is immediately after we catch a ball, it's thrown. So a ball is immediately thrown after it's caught. So if we try to get the beat that GIovanni's doing here, every time a ball's thrown and caught, that's a beat, so let's see. I also have no musical talent. But essentially, he's juggling along to a very, very fast speed where the ball being caught and thrown is essentially counting as our beat. A fourth thing that we're going to do is we really aren't too fancy. We don't care about hand motions. Hand motions are irrelevant. So even though GIovanni can do oh, this is a terrible talk because of you, GIovanni. So even though he may change the motion of his hands and how the balls are actually flying through the air, if you look at the time steps where he's actually catching and throwing the ball, that's remained the same no matter how his hands are moving. So combinatorially, when we interpret these types of patterns, we only care when the balls are actually landing and being thrown. We're not going to be caring about everything extraneous. And right there, GIovanni did something that we're not going to consider. So something that we're going to do to make our lives easier for this talk, even though we can definitely go against it, and there's lots of theory developed, is that a single ball is thrown. Ball is thrown / caught at every beat. We can't throw or catch multiple balls like he's doing there, where some of the balls are being caught and thrown at the same time. We're going to ignore that case for right now, as thrown and caught at a beat. So if we take all of these assumptions into account, we don't care about how the balls are flying through the air, we just care about how they're being caught and when they're landing. Sorry, when they're being thrown and when they're being caught. It leads us to say that really a juggling pattern is really just a bi-infinite sequence. It's really a sequence T0, T1, T2, so on and so forth, T-1, T-2, so forth, where are you getting food while you're juggling? Where the ball thrown at time I lands at time I plus T. So if I look at the spot where is the beat that I care about, essentially it's telling me how many beats into the future I should be throwing this ball. So for example, that pattern GIovanni was doing, he already sat down, I won't make him get back up, was a pattern that is 3, 3, 3, 3, 3, 3. each time the ball is thrown, it lands exactly 3 beats later, and that is repeated indefinitely. So the pattern GIovanni was doing was 3. But of course, in order to make our lives easier, we don't like infinite things. I don't like bi-infinite sequences. No, hell no. So we might as well think about doing things periodically. So one thing I should mention is that because of condition 5, a single ball is thrown and caught at the beat. These can't be any numbers they want. What we should have is no collisions. So what should be the case in order to juggle this, this is juggleable. If I plus ti is distinct from j plus tj for every I not equal to j. So what this means is that any time that that a ball lands, it is the only ball landing at that time, and we do not get a collision based on condition 5. So let's now restrict ourselves and pretend, instead of having a bi-infinite sequence, let's pretend that we repeat the same pattern every n. So what we're going to be dealing with is periodic sequences. Periodic. Which can be represented as a set of integers t1 through tn. And this is repeated every n beats. So how can I know, before I even start, if said sequence is even capable of being juggled, namely that condition 5 holds? Well, here we just said that all of the landing times need to be distinct. And of course here we're going to require the same thing, which is really just a modular condition. So what we do is we call such a sequence, we call it a site swap. So this is called a site swap. A site swap. If I plus ti mod n is distinct for every I. In other words, never in the life of juggling this pattern forever will we run into a collision. So this is the special modular condition that needs to hold, and it's juggleable if and only if we actually have this modular condition. And again, these t's are telling you how far to throw into the future. Did you have a question, Sam?
Do we have a notion of how many balls are out in the air at this point?
So yeah, let's talk about that, because I could write down any juggling sequence, and that's something that you could care about a lot, right? If I want to juggle this pattern, how many balls do I need? That's a fantastic question. So let's answer that question.
So we can hold on to many balls at a given time.
I'm sorry?
We're allowed to hold on to many
What do you mean
balls.
hold on to?
I mean, if I need k balls,
Well, remember, we've been juggling forever and we'll continue to do so. You don't have to worry.
Everything is in the air.
Yeah, so everything is in the air in what we're doing. We are not considering the case of actually starting juggling.
so could there be a concept of I would need, at this part of the string, I would need k balls, but at this part of the string, I only need less than k balls, so I'd have to be holding balls.
Well, that doesn't happen in what we're doing.
So that's just.
It's a periodic sequence, and the number of balls would already be fixed. If you don't restrict to periodic sequences, you could build a bi-infinite string that requires infinitely many balls, where essentially you just keep adding balls. But we don't really want to deal with that because, again, infinity is scary. You stay away from that. I mean, but yeah, let's talk about how many balls, because if I were to give you a site swap sequence and say juggle this, you check the modular conditions and know it's possible, how can you know how many balls you need to start juggling? This is a great little easy theorem, is that the number of balls needed is exactly the average of the TIs. Fantastic. So let's give a short little proof of this fact. So, little proof. It's going to be a double counting proof, where what we care about counting is essentially what I'll call air time. So we'll count air time. And by air time, what I mean is we're going to count the total amount of time that all the balls are in the air throughout juggling this sequence. So one way to count this is, well, there are b balls for some b. And based on one of our assumptions on how we're juggling, instantaneously, whenever a ball is caught, it's thrown again. So in other words, each ball is in the air the entire time. And the total time period that we're thinking about is n. So each ball is in the air for n beats. So in this case, air time is b times n. And to count this a second way, instead of thinking about each ball independently, what I can do is I can go to, say, the ith time beat and say, the ball that you throw right now, how long is that ball in the air before it lands? So air time can also be counted by simply going to each of these and adding them up. Because the ball thrown at time I is going to be in the air for ti beats before it lands, and then it's counted by something else. So by putting these together, we see that b is equal to 1 over n times the sum of the ti's.
Wait, except how do we deal with the modularity? Because like ti might be
Okay,
greater
sure.
than
So okay, maybe I'm lying to you then. So think about this. So the problem is this wraparound, right? So what we can do is we could say repeat this pattern multiple times until actually the period is longer than the highest throw. And now if you've repeated it that many times, you're sure to see every ball exactly what you'd want with the wraparound happening. So I guess technically you do need to do that, but I just like lying to you. I'm okay with that. But yeah, that's satisfactory answer. All right, cool. So this actually gives us a way, I mean, instead of checking all these modular conditions, which is, well, easy for a computer to do, but a pain in the ass to do by hand, well, this actually gives us a necessary condition for a certain sequence to actually be juggleable. In particular, if T1, Tn is a valid site swap, then the sum has to be 0 mod n. Great. That's a great necessary condition. It's a great necessary condition, so we can even rule out certain things without checking. For example, if I were to, say, consider a site swap that's like, I don't know, 1, 2, and ask if I can juggle this, the answer is no, because if I add it up, well, take 1 plus 2, this is 3, well, mod 2, this is not 0. So certainly, the average is not an integer, so how could I juggle this thing to begin with if I need a fractional number of balls? But of course, it isn't a sufficient condition. It's not sufficient. In particular, we can consider sequences, I don't know, something like 3, 2, 1. And if we check the modular conditions here, we see, well, 3 plus 1, mod 3, well, that's 1. 2 plus 2, mod 3, is also 1. 1 plus 3, well, that's also 1. This is a terrible juggling sequence because everything's going to collide right away. So this is not juggleable. It's not a valid site swap. Valid site swap. Even though the average is an integer. The average is equal to 2. So it's definitely not sufficient. But there's something that we can possibly notice with this sequence. If we were to, say, take this guy and just rearrange the throws, say instead of doing 3, 2, 1, 3, 2, 1, 3, 2, 1, let's instead rearrange them to be 1, 2, 3. Take the same numbers and just rearrange them right now. This is actually juggleable. We can check the modular conditions here. So if we check the modular conditions, well, 1 plus 1, that's congruent to 2. 2 plus 2 is congruent to 1. And 3 plus 3 is 0. So this is actually a valid site swap, even though a rearrangement isn't. So this is valid. And if you play around with this a lot, many of the time if you check an average, yes, the average is an integer, but this isn't juggleable, and you play around with moving around the actual numbers in this site swap, you'll find that you can actually always rearrange them into a juggleable sequence. So in other words, this condition of saying that you have to have an integer average is almost sufficient in the following sense that if you actually do have an integer average, there's some way to rearrange the number so it actually is a valid site swap that you can actually juggle. So to write this thing. This is often attributed to Hall, a third Hall, Marshall Hall, not Philip or Monty. So we have another Hall in here.
Are they related?
I mean,
Okay.
probably not.
Good.
They all were just born in a hallway. That's all there is.
When we all.
Yes. Hopefully not. I'd rather be born in a room. Theorem by Hall says that if the average actually is 0 mod n, so they add up to 0 mod n, then there exists a permutation pi such that the sequence t pi 1 up to t pi n is a valid site swap. So that's kind of interesting. So I guess in this talk I can propose a couple open problems if people actually care. I don't know. But one interesting question that you can have there, so a nice proof of this actually gives an order n squared time algorithm to actually give you a valid site swap from your original guys, and can be represented as, say, putting rooks on a chessboard is kind of the nice way to do it. But here's a question. If I give you a set of integers that do have an integer average, how many ways can they be rearranged in order to make a valid site swap? And this isn't known. I computed these numbers and stuff, couldn't find a pattern, and I was like, I don't care enough. But this is an open question and probably might have interest to people that actually do this math of juggling. So let's see here. So we have site swaps. We have. I also didn't prepare this talk, so we'll see where we're going to go from here. What else might be interesting with site swaps? Well, okay. So I have 45 minutes scheduled. Is that right? Like 10 till what? Oh, I'm not going to go. Okay. So here's a big question that we can care about a lot, is the kind of meta question. We're doing combinatorics right now. What's the biggest question in combinatorics? How many are there? So if I say, how many juggling sequences are there? Of period n using b-balls. Very natural question, because in enumerative combinatorics, the questions are always easy. The solutions aren't necessarily. It turns out that we could go through a lot of work and actually find the answer here. But it is a lot of work, and we wouldn't have time to do it in 45 minutes. You need lots of theorems, some weird stuff about Eulerian numbers, which count like drops and permutations. You need a lot of machinery in order to do it. But I claim that we can do it very, very quickly by reinterpreting juggling patterns. Instead of using these weird numbers, let's use something that may look a little bit strange, but works out great and also brings up lots of interesting questions on it. So let's think about another interpretation of juggling, namely what we call the card interpretation. So when we talk about cards, what we're going to be doing is we have a deck of cards that each have something on their face. And what we'd like to do is say that any way to arrange said cards actually produces a valid site swap and vice versa. So what are our cards going to be? Well, we have the b-ball deck. And what it consists of is b+1 cards, and I'll give you an example so we can see. Essentially, what we're going to do with the site swap interpretation, what we care about is that at this time, how many beats in the future is this ball going to land? That's what the site swap interpretation is worried about. The card interpretation is worried about so-called relative ordering of the balls at any point. So at any time, I could say keep juggling, and then take my hands back and look at the order that the balls hit the ground in. This is essentially, at that time that I take my hand back, this is the relative ordering that these balls have. Namely, this one would have hit my hand first, this one would have hit my hand second, so on and so forth. So let's think about that. for an instance. So let's take, say, 4 balls to begin with. Well, if we think about tracks, we have 4 tracks. Because 2 balls don't ever come down at the same time, so we know that there is an ordering for these balls. We can think about, well, if I were to take my hands back, whatever ball is in this track is going to hit the ground first. Whatever's in this track is going to hit the ground second, so on and so forth. So we have these tracks, I guess. And the cards that go along with it are how a certain move repositions the tracks. So for instance, the first card, well, no ball actually comes down into your hand. That's perfectly fine. I do nothing during that count. I snap or something, but no ball is actually down for me to throw again. In this case, well, the relative ordering of the balls should stay the same because I haven't done anything to these balls. Another thing I could do is I could actually throw a ball. 2, 3, 4. So the first ball comes down, I grab it, and what I can do is I could throw it so that even now it would still be the first ball to land. So in particular, I could throw it back into, say, the first track. It is still the first ball to land. I have not even touched the other balls, so they stay in their same tracks. What else could I do? Well, the ball that comes down, I could say put it into the second track. I could throw it so that after that throw, it is now the second ball to land. So this is maybe a bit strange because how do I know how far to throw it to position it into this track? Well, you don't. But again, this is a different interpretation that'll help us count something. So what happens if I do this? Well, now whatever was the second ball now becomes the first ball. And the other 2 balls remain unchanged. And I can keep doing this. This is the whole idea of the cards, is how do I position the ball using this? So I could also throw this ball into the third track, in which case the second ball now becomes the first, the third ball becomes the second, and the fourth is unchanged. And finally, the last card in this deck would be positioning it into the highest track. So if I actually put together a bunch of these cards, it will give me a valid juggling sequence, reading it with some wraparound, and vice versa. So let's think about this for a second. If I were to say, give you 1, 2, 3, and let's say a 5-card sequence, let's draw some cards, and I'll show you how it corresponds back to a site swap. So I don't know, maybe here, I don't know, we throw it to the second position, here we're going to throw it to the third, here we're just going to reposition it right here, we'll throw this one all the way up, and we'll throw like this one all the way up. So we can give you a set of cards, and what I want to claim to you is that this is actually a sequence of n cards gives us a b-ball juggling pattern. So let's try to figure out the site swaps that we're using here. Well, the ball that I threw here, when does it land? Well, it lands 1, 2 beats in the future if I follow the track. So the t here, the number of beats into the future I threw it was 2. Here, if I look at when it lands, 1, so I'll follow it 1, 2, 3, 4, 5. And it's 5 beats into the future because we're doing everything with wraparound. Here it lands 1 beat into the future. Here we go, 1, 2, 3, 4, 5, 6. And the last one, 1, 2, 3, 4, 5, 6, 7, I think. I may have gotten some of those wrong. But the idea is that if I were to give you a bunch of cards, I can read off the corresponding site swap. And it's more difficult to do by hand, but it should be obvious that if I give you any site swap, obviously there's a cards thing that goes simply by, well, at any time, what is the order that the balls would land in? So one direction of the bijection is obvious, and this is how to do the other way around. Questions about this? Yes?
So this will not have period 5, though.
It does have period 5. Because this pattern, the site swap is repeated every 5 beats.
But it might be like a proper multiple of 5.
What do you mean?
Because look, when we follow the first ball all the way around back to the first card, you're not.
But now it's the third ball, right? Is that what you're saying?
Yeah.
We'll actually talk about that. That's a good point. But when it comes to site swaps, you would have also had the problem with the site swaps, right? Even if it's period, I don't know, 12, it could be that the ball that you threw at the first time was not the ball that you threw at the second time, right?
Okay.
We never made any, we had no problem with that when it came to site swaps. All we're saying is that this is in bijection. But that question that you asked is a very good question, and I'll actually answer that exactly for you. Yes?
Does the number of sums should be the 0 modulo? Like
Yeah, it
1?
should. Did I make a mistake?
Yeah, but I mean, it's not. Right?
It's not. Did I make a mistake on
It's
doing these? I could have just made a mistake counting. This one is 2, 1, 2, 3.
Counting is your job.
I can oftentimes only count when n is sufficiently large, Wilson. I mean, Monty, sorry. Yeah, obviously I'm racist. That should be a 4. I think this is a 4, right? Does that fix it? But yes, I can only count when n is sufficiently large. I don't do a numerative combo. Fuck that noise.
Wait, no, it's not gonna be 4.
No, it's not.
Like, I think it's 9.
1, 2, 3, and now it's right there, so it is 4.
Wait.
The 1 is fine. The 6 is 1,
Oh, when it comes down.
2, 3, 4, 5, 6. I think this is right now. Hopefully. But anyway, you can count this. I just can't count small numbers. I can count numbers when they're sufficiently large. Because lower order terms don't matter, and I think, you know, like a 1 is a lower order term. So we're okay. So this is the thing, is that any placement of cards coming from the b-ball deck of length n corresponds to a juggling pattern of length n. So if I want to answer this meta question, how many juggling sequences are there of period n using b-balls? Really all I'm doing is counting how many ways I could have placed down the cards. In particular, there are b+1 cards in the b-ball deck. Simply because we have the do nothing and then the put it in the first, second, third, all the way up to the bth track. So how many ways would there be to lay down n of those cards? b+1 to the n. Fantastic. But that's not quite the answer. Yeah, did you?
I'm sorry, but I don't understand why we need the do nothing card.
Well, because at some point you could imagine, like, I threw the balls up really high, and then I just wait for them to come down. I'm not doing anything in that time, right? I'm not throwing a ball.
There's a beat though.
Hmm?
There's a beat.
You can throw it really high into.
Well, what I'm saying is there is a beat, but I am not touching a ball at that time. It's possible that there is a time where simply all the balls are in the air and I'm just snapping my fingers. I've done nothing to touch these balls. But I also
So when that happens, what do you do for the side swap?
Oh, it would be a 0.
It would be
Because
0, okay.
because if those T's could have been 0 at any point, and that is essentially a do nothing time beat, where no ball is landing and no ball is being thrown. It still works out perfectly
You don't
fine
have
with
to
the modular.
consider T's being 0 being allowed, right?
You don't have to. If you want to throw it out, great.
And then there's just B cards.
There are just B's. So yeah, if you don't want to have a 0 throw, we can modify. But I'm also saying this isn't quite the right answer.
Okay.
Because the one big reason it's not quite the right answer is, suppose that I never used this card. I never used the card that put a ball into the very highest track. Well, in that case, what would happen is that the very highest card would just stay constant. It would never come down into my hand. It would simply be floating up there forever. Or, in other words, essentially, I'm not using this ball. So if I want to know if I want to use exactly B balls, well, I should just subtract off the number of ways that that happens. Minus E to the n.
Wait, but you don't like infinity, so how can you do that?
Well, like a ball staying in the air is essentially just a placeholder. Nothing's actually happening.
0 G juggling.
Hmm?
0 gravity juggling.
Sure. That would be interesting. You'd have to be like on both, tossing them back and forth. I guess this works.
You could do this, dude.
It works. Like something like this works. So this would be our answer for how many juggling sequences are there of period n using exactly b balls. b+1 to the n minus b to the n. Now, of course, you may say, hold on a minute, we're doing periodic things, you know. How many of these are actually just shifted periods? Yeah, we're absolutely overcounting with this thing because we're counting cyclic shifts of all of these separately. But of course, I will say, with Mobius inversion, you can get rid of this. It's just, the formula is not as pretty. Because you have the gross sum with a Mobius function in it, blah, 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 all stuff that we know how to do. But it's not interesting. So this is our answer. So that's pretty cool. You have to do a ton of work to get this same answer with the side swap interpretation. But now let's go back to Andy's question. Andy had this. So Andy pointed out something that we didn't really notice when we were just dealing with side swaps, even though it was the case. That right here, the ball that I threw right now, if I say label the balls 1, 2, 3, 4, well, if I look at what happens after each card, namely now this is the second ball, this is the first, third, and fourth. This is now the first ball, third ball, second ball, fourth ball, still the fourth, this is still the second, third, 1, 3, 2, 4, 1, and then we finally get 2, 4, 1, 3. So if we go back and we were to say wrap around on the sequence, the ball that was originally in the first track, well, it's a different ball in the first track now. So Andy was questioning, well, do we really get to wrap this around? Well, yes, if I only care about how I relatively position them. But what if I also want to make sure that the balls themselves follow the same period? So I'll call these wraparound card sequences, I guess, where actually it is legitimately period n, because if I wrap it around, the balls are in the exact same tracks as I would expect them to be. So we could ask the following, is how many wraparound card sequences are there? Well, the way to realize how many wraparound card sequences are there is this is the exact same thing as requiring that the permutation at the very end is the identity permutation. We can think about each of these cards does some sort of permutation to the balls. Really, this is questioning how many ways to end with the identity. So this is equivalent to how many ways to end with the identity. This seems like a hard question, because you're saying, well, if I fix the identity at the end, how many ways can I get there? But these permutations are kind of a bit strange. You only have access to certain permutations in the symmetric group, namely these cards are all just their own permutation, which has like a single cycle and a bunch of fixed points. But it turns out the answer isn't too bad, and we can write the answer as, let's say, I equals 0 up to n choose I, and then n minus I, and this is not very good notation, but I'll define what I mean by this. This thing, I'm using the Stirling numbers of the second kind braces. So what I mean by this is the number of ways to partition, I guess in this case, bracket n minus I, into at most b non-empty parts. So usually Stirling numbers of the second kind, I just have a b there, and it says exactly b non-empty parts. But here I'm actually going to allow you to do as few as you want, but you're not allowed to have more. So how do we prove this? Well, let's think here for a second. What we want to do is essentially really the changing thing is this n choose I, the I. But what that corresponds to is when I actually use the 0 throw card. So let's give one direction of the, we'll first do the easy direction of the punctuation. So if I give you, if you have a wraparound, actually if you have any card sequence, it actually gives you essentially this number. So if you have any card sequence, actually, let me just give you an example. It's kind of not easy to write it. So let's go back to this example right here. And I'm going to change, so I'm going to change a couple things. Okay, I lied to you. I'm going to change like everything. is what you get if you don't prepare. And then we'll just like make up some stuff. This is just going to be 3 balls. This one's going to be a 0 card. This one's going to be flaw, and then something like that. So if I again label the balls that are thrown at each time, I can partition into something. Namely, this is special. I'm going to color this card purple. And every other card, I'm going to equate it to the ball that is actually thrown at that time. So let's think about the balls actually thrown. So if we started with the idea 1, 2, 3, 4, the ball thrown on this card is ball number 1. What ball's thrown at this card? Also 1. The ball thrown at this card is the second ball. And the ball thrown at this card is...
There's only 3 balls.
I think that's
Oh, that's 3. And this doesn't really follow our pattern at the very end. We should have some wraparound, right? If we were to end with the identity, which I was bad at. But the idea is to get this partition, everything that is not a 0 throw, we can basically put it into a group based on what ball is thrown here. So I can say color all the 1s with blue, can color the 2s with yellow, and I can color the 3s with, say, green. And what we have is we have placed some number of purple squares, and the rest of it, bracket n minus I, has now been partitioned into some number of non-empty subsets based on the ball that's actually thrown at that point. So at most B non-empty subsets.
Wait, why is it not exactly B?
So imagine if we never used this highest card, right? It could have been that I will never throw the ball in the highest track, right? So if I said never would I ever have thrown 3.
We're just counting card sequences.
Yeah, we're
not
counting card sequences.
Okay.
So if I never throw the card that's in some track, well then I'm not going to have a partition corresponding to that card. And this is exactly how we get the bijection, is how do I undo this? So if I were to give you, 1, a number of purple squares telling me where I don't have a throw, and I partition the rest of the cards into some number of things, can you actually reconstruct a card sequence which ends with the identity? And this is the trick. So let's do something long and we'll walk through how it works. So like 1, 2, 3, 4, something of this length. So we'll have some crowd participation. So the n choose I is choosing where the purple squares are. Where do you want the purple squares? Let's just do like maybe one of them. I don't know, somewhere. We're going to put a purple square here, just because. So that's like 1 purple square. And now what we have is the rest of the cards are now partitioned into, let's say that we have, again, we can do 4 balls. So give me a partition of the rest of them into sets, at most 4 of them. I don't know. We'll again use some colors. Yellow, we have blue, we have green, and red. What color should this card be?
Wait, are these labeled or unlabeled partitions?
Unlabeled.
So then we can't assign the colors yet.
Well, the colors tell you just the partition, that they are in the same thing. I'm not saying that this is the blue partition. I'm saying that if I looked at the partitions,
okay.
this would correspond to 1. We have, so this is card 1, 2, 3, 4, 5. The purple is saying, well, only 3 is in that set. And then we also have the partition, which is, well, 1 and 2 are in the same. 4 and 3. So this would be the corresponding kind of partition that we get. Again, this is a bad example because we don't actually end with the identity.
Yeah, so I guess I'm confused. If we have this bijection and you wrote down that, why didn't it wrap around?
Because there are a few reasons. Let's change it so it actually, we can change it so it does wrap around. All right. I think now it wraps around, right? But yeah. The reason is because like if it doesn't wrap around, I might not actually get this right type of thing. I just did a magic. But certainly if I wrote down a card sequence which ends with 1, 2, 3,
Oh,
4,
I see.
with 1, 2, 3, you will get this thing by looking at what ball is thrown at what card. The problem is if it doesn't wrap around, I could have wanted to throw ball 3, but I won't see ball 3 in the period itself, right?
Okay.
So let's think about it. So what color is the first card?
Yellow.
Yellow. Second card? Green. And we don't have to use all 4 colors if we don't want to. Next card?
Red.
Red. Great. Next card?
Yellow again.
Yellow. Next?
Yellow.
Yellow. And finally?
Yellow.
Yellow. Where did my yellow go? There's my yellow. Great. Fantastic. So again, the colors, these subsets, they aren't actually labeled, but the colors are just saying that these were in the same subset if they get the same color. So I claim that with this, we can actually reconstruct for you a card sequence which ends with the identity. So that ends 1, 2, 3, 4, and starts with 1, 2, 3, 4, by filling in the cards. So the easiest card to fill in is the purple card, because we distinguish what purple meant. It meant that everything stayed the same. It's our do nothing card. But how are we going to make sure that if we kind of throw the ball, it ends in the right place? Well, the first thing I can do is that we can actually label these subsets uniquely. Because if I'm going to throw the second ball, I have to have first thrown the first ball. There's no way to throw the second ball without having thrown the first. There's no way to have thrown the third ball without throwing both the first and the second. So on and so forth. So I can actually tell you that yellow corresponds to throwing ball 1. Green corresponds to throwing ball 2. Purple corresponds to throwing ball 3, and we never throw ball 4. So that means that on these cards, I also have to throw 1. Now let's make it more interesting. All right, so this, I have to throw ball 2. Now the trick of finishing off with bijection is not to work your way forward, but to work your way backwards, because we know what we want to end with. So here, and this also makes our lives a bit easier. Let's put some dashes. Here, I had to have thrown ball 2, which means that there's only one card that I could have had, because I know where ball 2 ended up, and I knew it had to come from the first position, because that is the ball that I actually threw. Here, I have to throw ball 1, which is right here. So I can uniquely fill in this card. Here I also have to throw ball 1. Where is it? Here I have to throw ball 3, and that's right here. Here I have to throw ball 2, which is up here. And finally I have to throw ball 1, which is up here. And we're happy. Everything's been put back into order, and this is how to complete the bijection. So certainly, if we have wraparound, then each card corresponds to a unique ball being thrown, or no ball being thrown. Because no matter how much we wrap around, we're always going to see the exact same balls, which was the whole point of asking for wraparounds. And finally, we can reconstruct it by working our way backwards.
So this means that there will be a problem. There exists some partition that will get us into trouble if it's not the wraparound sequence at the end, because
yeah.
it exactly counts the number of things.
Yes. So my first example. No, what you really get is that if you don't have wraparound, then actually some of these partitions will be counted multiple times, or the partition doesn't actually make sense. And what this shows you that if I know I have wraparound, then it corresponds to a unique partition and the special purple blocks. So it's in bijection, but if you don't have wraparound, it still corresponds to one of these partition things, or maybe it doesn't make any sense. But then it's just overcounting, and we've restricted our space.
Okay.
Does that answer your question? Well, like the one I had earlier had a perfectly fine partition, right?
Yeah.
But it wasn't wraparound. That's fine. I mean, we only care about having a bijection between the number of these partition things and the wraparounds. So sure, multiple card sequences in general can correspond to the same partition structure. But yeah, if we restrict ourselves to these wraparounds, it is a bijection, which is pretty nice. Okay. So again, thinking about these cards, I want to introduce one more notion with these cards, which is something that is a completely open problem. I'll show you the one thing I know about it, and then say, well, if you're interested, let's go for it. So let's actually look at the permutations after every single card. Namely, this permutation, we get 2, 3, 1, 4. I guess 4 is always at the top. So on and so forth. Here, 2, 1, 3. That's now 3, 2, 1. 1, 2, 3. 3, 2, 1. Okay. 2, 1. Blah, blah, blah. We can look at the permutation of the balls after every single card. And what I'm interested in is finding ones where every permutation shows up at most once. So let's talk about these. So we'll define them. A prime card sequence is a wraparound sequence where each permutation is seen at most once. So in this case, this is not a prime sequence, because first of all, well here, I see the same as the very beginning. Oh, I should say the same except for the beginning and the end, because again, we think about this as wrapped around kind of on a cylinder. So the very, very end and the very beginning are essentially exactly the same. So here, this is not prime because I happen to see this permutation, well, 3 times. Now I've seen the identity 3 times. I'm sure I see some of the others multiple times as well. 4 times, blah, blah, blah. This is not prime. But what if I'm interested in seeing each permutation at most once? How many ways are there to do this? And I have no idea. This is a question. So we can define, say, P of B comma n to be the number of these. Well, there are some obvious bounds. At least we know some places that it's 0. In particular, PBN is equal to 0 whenever, n is strictly bigger than b factorial. Number of balls being b, period being n. Well, if I have more cards than they're all permutations, then I obviously can't be prime. You can also get some other really silly bounds for some other ones. But I'll show you the only interesting thing that I know about these prime sequences. And that's that what if I were to ask you how many prime sequences are there with b balls and b factorial minus 1 cards? So we're missing exactly 1 permutation. Turns out there are none. This is 0 for every b at least 3. The reason it's silly for 2 is that then we're only asking for 1 length card sequence. There are 2 of those, right? Either the do nothing or the just put it back into the position 1. But for b at least 3, it's impossible to be missing exactly 1 permutation. Which is kind of interesting. I was surprised by it when I computed these numbers on the computer. Well, let's prove it. Now the key is, if b is at least 3, then b factorial minus 1 is at least 2. That works. Great. So b factorial minus 1 is at least 2, so we know that we have at least 2 cards inside of our prime sequence. So this actually tells us something, not about the permutations we see, but about the types of cards we use. This actually tells us that we never use 2 of the cards. We never use the do nothing card, because the permutation is the same at the beginning and the end if we do nothing. And we also never use the throw it back into the same position card, because again, we have done nothing to change our permutation over that card. So we know these are never used. In particular, we never throw the same ball twice in a row. Same ball. Twice, 2 times in a row. All right, so now let's think, suppose we did have a prime sequence of length b factorial minus 1. that means that there is one permutation that is missing. Right? There's exactly one of our permutations that's missing. So let's suppose the missing permutation has ball I on the bottom. So in other words, if the permutation we're missing, we haven't actually thrown that ball. So, but I do see every other permutation that does have I on the bottom. So let's count the number of times I throw ball I. We threw ball I. Well, this is exactly b minus 1 factorial minus 1, because we throw ball I whenever it is at the bottom and is the next ball to be thrown. But now let's think about this. We never throw the same ball twice in a row. So if I were to say, have my permutation have some I and then J, so on and so forth, ball I is thrown at this card. What ball has to be thrown at the next card? J. So another way to count the number of times that I'm going to throw ball I is to look at the number of times that it's in the second position with the wraparound. So here we're definitely using wraparound. So how many times should I have thrown it? How many times is it in the second position? b minus 1 factorial. So we should have thrown it b minus 1 factorial. And this is simply because every single permutation that had ball I in the second's coordinate is there. So I should have actually thrown it b minus 1 factorial times, but I didn't, and that's our little contradiction here. And this is literally the only thing I know about prime card sequences. But if anyone's interested, you can do it. The numbers don't fit into OEIS anywhere, so that's all I can tell you.
Oh, it's because we don't use that.
Because we never use
Yeah.
either of these two cards. I can't throw the same ball twice in a row. So because I have this wraparound property, cyclically, if I look at the second ball in that card, it has to be thrown next.
Weird.
So I see this ball in the second position more times than I actually throw it, which is impossible. And that's all I have to say. Great, Giovanni can juggle more if you want it. Oh, you have a question, Sam?
No, it's in flat.
Oh, okay. Awesome.
Any questions?
What about just b factorial, just all the permutations?
There are a bunch of them.
Like loads, okay.
I mean, there are a lot. Again, I could only compute the data up to a certain point because it's big and you run into recursion depth problems. At least my computer. And I also suck ass at coding, so there could be a better way to do it. The only other interesting thing, so I got this out of the code and tried to explain it. I could. The only other thing that's weird about this is that it's not unimodular. If you look over fixes and look at all of them. When you get up to b equals 4, you actually get some like spiky behavior. You don't actually get unimodular behavior. And that to me, the only thing it can say is that there's some divisibility criterion going on. But there are a lot of length b factorial based on the numbers I can't compute. Yeah.
How many is a lot?
More than 5.
Like, sort of just plugging them into, oh yes, but like...
As in, it's definitely more than exponential growth, it
Okay.
seems. It seems. Yeah, no, these numbers up to 4 were already in the hundreds of thousands. So yeah, lots. More than 5 is lots though, Joe. You and I work together, we know that we can't go past like 6. Well, you always want to, and I never let you. Yeah, Kevin.
What would be the generating sequence of? I guess it satisfies some, but the generating sequence.
Generating function
Sorry,
of it?
generating function, sorry.
Generating function of,
Let's say.
well, I mean, these numbers don't fit into a nice pattern, and also the generating function would be weird. We have two parameters, right? So you can think about a 2-term generating function, but again, these numbers don't fit into any sort of pattern on OEIS. So I can't tell you that. One way to try to get a handle on these numbers would to be to try to find a 2-term generating function. And honestly, because these numbers don't show up on anywhere on OEIS and they don't match up with any generating functions that are in OEIS, it's probably the best course of action is to try to come up with a two-term generating function just to get a handle on even asymptotic growth. Does that answer your question? I have no idea because I don't know what the numbers are. And I can compute the numbers, but I don't know how to make the generating function for them.
Or how does the generating function, does it satisfy itself?
I have no idea.
No, I mean, the property, is there a solution to something you need to the calculation to help?
You can do that yourself, Kevin. I don't know. I mean, if someone wants to look at it, be willing to look at it with you. I have absolutely no clue. As I told you the one thing, I also have a really terrible upper bound on how many there can be in terms of Stirling numbers, using the same idea of those partitioning everything. You can use that to get an upper bound, but computationally it's absolutely terrible. The upper bound is so much bigger than this, but that's all I can do is show you this and give you a really terrible upper bound. I don't know anything else about this.
Did you also mention some suspicious behavior of the function when we take some special values, like when...
No, I can only, my computer's only been able to do up to b equals 4. And the only difference is like, you need b at least 3 here because otherwise,
Yeah.
with 2, it's a 1 card, so you can't actually use these 2 cards. So you get like 2 for when b equals 2. That's the only weird case,
Okay.
is that if you have length 1, then there are always exactly 2 of them, and that's using one of these 2 cards. Anything else?